So. For as undetermined reason. Objective's not working. At least it wasn't working when I was teaching class earlier and we tried to fix it and we were not able to. Yes, yeah, it's really not good, yeah. So, and instead is up on the board. Hopefully you all on Zoom can see the board pretty decently there. Also, my plan was to go over a final review that I posted on Canvas. So if you all go to, if you want to, you don't have to follow along, obviously. If you want to go to Canvas and scroll down to like the last module that has some final review materials, you'll see the final review. I can also hand that to you all. Let me just show you all if you want. A second. Okay. Sure. If you go to Canvas, scroll, if you go to the modules, and scroll down to the bottom, you'll see a 17C final review right there. So you can look at that if you want to, although I'm going to write the questions anyway, so either way is fine. Cool. So, great. Also, I posted an announcement that has my office hours for next week for when I'm in drop-in. So if you're looking for me specifically, you can find me there. You can also find just when all the office hours are for drop-in next week.
Is that in the library?
It's in the library. Yeah. Everything's in the library.
On Tuesday, I wasn't here. Did you go over homework setting?
I might have gone over some of them. We can certainly look at some stuff from homework 7 as well, if you all would like to. I believe I grabbed myself a copy. Yeah. Are there any? So this goes for people on Zoom as well. Are there any questions from homework 7 that we should address? Sure.
It says a bag contains 9 red marbles and white marbles.
Sure.
And 9 blue marbles.
Yep.
Draw 5 out at random without
Sure.
replacement. What is the probability that all marbles are red?
Sure. You can look at that one. You're welcome. We're looking at some homework problems. I'm gonna grab the chat too. Sorry. Yes, we're looking at the first problem from homework 7 real quick here. It is. So generally, we'll find a probability. It's the number of ways of getting what we want divided by the number of ways of getting anything. That's usually what I'm keeping in my mind when I'm thinking about how to calculate a probability. Let's see what we've got here. Good old shock is what we've got. So, oh, sorry, let's see where we go. Right over here. We got a bag with 10 red marbles and 9 white and 9 blue. We're going to draw 3 and without replacement. And we want to know what's the probability that all the marbles are red. That's the first question anyway. So first question, I'm gonna write it this way. What's the probability of drawing 3 red marbles? Okay. So how many ways can you draw 3 red marbles? It feels like kind of a weird question because you might feel like the answer is 1. That well, I draw 3 red marbles and they're all red and there's only one way to get 3 red, but that's not really true. If we number the red marbles, right, there's really 10 different red marbles. Maybe they don't all look the same, right? Maybe one's like super red and one's like a lighter red, but they're all quote unquote red. So you've got red marble 1, red marble 2, red marble 3, so on and so on and so on, all the way to red marble 10. So of those 10 red marbles, let me ask a different question. What if I was just drawing one marble? So what if I said, what's the probability of drawing one red marble? Well, how many red marbles are there? 10. How many total marbles are there? 28, I think. So if I'm writing this in a very specific way, you can see it, yeah. So I'm writing this as, well, out of the 10 red marbles, I want to choose one of them, which is equal to 10. And out of the 28 marbles total, I want to choose one of them. If I want to find the probability of getting one red marble, it'd be 10 choose one out of 28 choose one, which is just 10 divided by 28. And is this notation familiar? Okay.
So do you put it as like the total amount for like a selected over like the whole?
Right. And the words I'm really thinking about saying are, I'm thinking of the total number of ways I can get one red marble. Or in this other example, the number of ways I can get 3 red marbles. So if I want to find the probability of getting 3 red marbles, well, the number of ways of getting to get 3 red divided by the number of ways to get any 3. Well, the number of ways to get 3 red is going to be right. And the number of ways to get any 3 is going to be 28 choose 3. So it's usually not too terrible in a marble situation if you're being asked to find the number of ways of picking an exact number of something.
And those are just fractions, right?
What do you mean?
Like if I had to put that into web work, it would be.
There's no nice way to write it. It's not 10 divided by.
No.
So 10 choose 3 is something. So right. So there's a few ways you can calculate this using a calculator. If you want to just type it in web work though, what you have to type is the following. So 10 choose 3 is, that's not what I want, right? I don't know. That's a good question. I don't think so, but I don't actually know. Yeah, I'm curious. I wonder. You should. So yeah. So the way you would write this using notion is it's always the 10 choose 3 is going to be 10 factorial divided by 3 factorial and the difference between them, which is 7 factorial. And then 28 choose 3 is the same deal. It's 28 factorial divided by 3 factorial and the difference between them factorial.
But I know if you put it into the calculator,
Right. Well, and the calculator most calculators do have a choose button on them. A lot of them anyways. So this, you can't see it though because I don't have them, sorry. So there is usually an NCR button on your calculator. But you can also just input this, and it's not fun to type this in, but you could. You can also do a little bit of simplifying here, right? I mean, this simplifies as 10 factorial over 3 factorial times 7 factorial times 3 factorial, 25 factorial over 28 factorial. And then 3 factorials cancel. And 10 factorial over 7 factorial is really just 10 times 9 times 8. And 28 factorial under 25 factorial is really just going to be a 28 times 27, 26. That's what that should turn out to be.
and this is combination.
It's a combination, because we don't care about the order we pick the marble.
And then permutation is.
We do care about the order. Yeah. Right, I don't care about this red marble first and this other marble second or vice versa. So, other questions about what we've done here? Yeah, definitely important to remember that this choose function, 10 choose 3, or more generally, n choose k or r, depending on how you want to write. I usually write k, but calculators use r. Is just n factorial divided by k factorial, and also the difference. Factorial. Right, so. Same idea. If you want, and I'm gonna write over here mostly so that people want to see, because we've got a situation here, right? You guys can see all right on this board here, I think so, hopefully. What's that? Yeah, the projector was not working this morning. I was in my other class, I'm not writing the board, but I've got the document camera so that they can see mostly what's on these first two boards here, so, yeah. Yeah, it was this whole situation. So what about the probability of getting 2 red? I'm still picking 3 marbles. Okay, so again, it's the number of ways of getting what I want. Two red divided by the total number of things that can happen, which is still the same as before. So the denominator here is still 28, choose 3. This situation, I feel like, is kind of similar to like whenever you talk about poker hands with 5 cards. And if you're finding probability there, you're almost always dividing by 52, choose 5. Because the total number of possible 5-card hands is the number of ways you can pick 5 cards out of 52. Okay, so I want 2 red marbles. There were 10 red and 9 other colors and 9 other colors, right? Yeah, okay. So how many ways can I pick 2 red? Right, exactly, 10 choose 2. But then I'm still picking 3 marbles. So there's still 1 marble left to pick. Out of how many can I choose from? Right, because I want to pick 1 more marble that is not red. So from the 18 not red marbles, I'm going to choose 1 of them. It's worth knowing that whenever you do something choose 1, you just get that number. So 18 choose 1 is just 18. Which makes sense, because if you've got 18, right, just like we talked about picking 1 red out of 10. There are 10 ways of doing that. You pick that one or that one or that one or that one. That's it. So, what if instead I'm gonna ask a different question, even though we'll look at it. What if I want to find the probability of picking 2 blue and 1 white? Well, same idea. We're still just counting the number of ways of getting what we want. So the number of ways of getting 2 blue is going to be, and the number of ways of getting 1 white is going to be, and the number of ways of getting any 3 marbles is going to be 28, choose 3. Now this last one's a little bit different. Oh, it's not really. Kind of. I don't know. Sure. So you should be prepared on your exam, I would imagine, to have some sort of question that involves using the complement. Okay, question, sorry. Right. Yeah. Yeah, and it wouldn't really. There's not really a good or question here, so there isn't really. That's not true actually. The next question is an or question. So the next question on this one is probability of no red marbles. Probability of no red. So there's a couple ways of doing this. You could either say, well, you have options, right? Because no red means you could, so you could think of it as, well, no red is going to be either 3 blue. No, I feel like I'm making it too complicated.
The first question was all the money.
Right. No, because so 1 minus that would be, so let's actually talk about that. So I'm gonna answer a different question first. What if I want the probability of at most 2 red? One way of calculating this would be the following: add them all up. That's the probability of 0 red plus the probability of 1 red plus the probability of 2 red. Which is what we're gonna answer here. It's fine. So 0 red. You could do this, although you don't need to. Say, well, the probability of getting 0 red is I want 10 choose 0. I want 0 red ones. And then from the other ones that are not red, I want all 3 of them. So from the other 18, I want to choose 3 of them. Divided by 10 choose 0 is just 1. Anything choose 0 is always just 1. Because you're asking what's the number of ways you can pick 0 things out of 10 things. Well, there's one way you can pick 0 things out of 10 things. You don't pick any of them, you pick all the other things instead. And then, so this would be the answer to the question that was actually asked. That's the way of picking 0 reds.
What's the equation above it with the P probability 1 red and 2 red?
This one here?
Yeah.
So this is the same, this is what this is. The question I'm asking instead, 'cause it's more interesting, is what's the probability of getting at most 2 red marbles? So at most 2 red would be, well, we could have 2 or 1 or 0. So it's an or situation, so we're adding these together. And then we would add probably getting 1 red, which is going to be 10 choose 1, right? Out of my 10 red, I want 1 red, and then 18 choose 2. Still divided by 28 choose 3. And then finally, if I wanted 2 reds, I already calculated that. So we 10 choose 2, and 18 choose 1. Out of 28 choose 2. Well, because there were 10 red marbles, there were 9 blue marbles, and there were 9 white marbles. So if I want 0 red ones, I want 3 not red ones, which is blue or white, which there are 18 of.
Oh, no, never mind. You said that, so like the box with the no red.
This is the answer to that question. Yeah. Now, the question that. Oh, yeah. So what I wanted to point out is we did this question that I just made up kind of the long way. Because another way of answering this question, the probability of having most 2 red marbles, you could have said, well, that's the same as 1 minus the probability of having all red. Because when you add up all the probabilities of every possibility, and having 0 reds, 1 red, 2 red, or 3 red encompasses all possibilities. If you pick 3 marbles, you have to have one of those 4 things happen. No reds, 1 red, 2 red, or 3 red. So if you add up all the probabilities, it should add to 1, meaning these 3 things together plus that should add up to 1. Or in other words, these 2 things should equal 1 minus the leftover thing. So we could have calculated this as 1 minus 10 to 3. And if you calculate these either way, you should get the same answer. They're kind of a pain to calculate, but they're not too bad. So hopefully that helps clarify how that first question was worked. So, well, how many marbles are we picking? 3. That's this right here. Probability of 3 red is this here. Out of the 10 red, we're choosing 3 of them, and out of the 28 divided by the total possibilities, which is out of all 28, we're choosing.
Oh.
Yeah. We could totally, I mean, you could ask other questions, so I guess we could change it to be like, okay, well, what if you've got 5, now you can decide I want to take 7 marbles instead of 3. What's the probability of getting, I don't know, 6 red ones? Same exact idea. But now we're saying, okay, well, how many red ones are there to choose from? Still 10. 10, choose 6. And then we still need to pick one more because we want 7 marbles total. So the other thing is going to be we choose 1. Still divided by, well, not still divided by, now divided by 28, choose. Really remind everybody, these aren't fractions, right? 28 choose 7 is not 4. 28 choose 7 is a much larger number. So there's one to factorials here. Now, if I were taking an exam and writing this, I would leave my answer this way, unless I was specifically asked not to. And even then, I would still leave it this way, go do the rest of the test, and then if I have time, come back and simplify. But really, don't simplify these choose functions unless you really have to or have the time. Just a little bit. Sorry, I know it's a lot of James there, but yeah. Okay. Say here. Versus, okay, what's the probability of at least 2 red marbles? I want you to, I'm letting you work. So if we want at least 2 red marbles, we can do the probability of, well, 2 red plus the probability of all the way to the probability of. That seems like a lot of things to calculate. What might I do instead? 1 minus the other things, which is what?
0.
Right, exactly. You can do that, or you can do it as 1 minus the probability of 0 reds plus the probability of 1 red. All right, I want you all to take a minute, try to write this down. Write down what that would be. 1 minus probability of 0 reds and probability of 1 red. I should say 4 probability of 1 red. And give you a minute or so. Those of you on Zoom, here's the attendance link again. Not good, I'm still on camera. I can see too much myself. Yeah.
The ones like these, there's 2. Here, you just like write it out like that.
Yeah, totally. Yeah.
And I can't really cancel things.
Well, that's not actually true. We can cancel, but now the thing is, the question is, do you need cancel stuff? I don't know. Like you could, but you could also just do. But I'll look at this and think talk about how we could simplify a little bit if we wanted to. No, well, we're choosing 7. We're sorry. We're in a 7 marble situation. I apologize.
That's all good.
We still have the same number of marbles, still 10 red, 9 blue, 9 white. So let's see, if we calculate this, is going to be 1 minus. The probability of 0 red marbles is going to be, I don't really need to write the 10 choose 0, but you could write the 10 choose 0. It's that kind of nice to see the whole process, because really it's just out of 10, the number of red ones you want. Out of 18, the number of not red ones that you want. Divided by out of 28, the total that we're picking. And the same deal over there. Out of 10, the number of red ones we want. Out of 18, the number of not red ones we want. Out of 28, the number of total that we're picking. And I would leave it like that. So just as a kind of, yeah, just for your kind of awareness, if you wanted to simplify something like this because you actually needed to, here's what I would point out. And let's just pick, I don't know, let's pick back there. What if I wanted to simplify? Yeah, that's not great. Let me pick something different. Let's make it more fun. Let's say I wanted to find the probability of getting Yeah, let's say 4 reds out of 7 marbles. And someone said you have to simplify this thing as much as you can. Because, I don't know, pain. Someone was not feeling good when they wrote the exam, they're like, I'm gonna make it hard. So first of all, this would be 10 choose 4. Oh, and then 18 choose 3, that's gonna be fun. Over 28 choose 7. Okay, so here's what I recommend. Treat them all individually. So 10 choose 4, 10 factorial, 4 factorial, 6 factorial. 18 choose 3 is 18 factorial over 3 factorial, 15 factorial. And dividing by this, I really don't even want to write this because I'm going to flip and multiply, but I'm going to write 28 factorial over 7 factorial, 29 factorial. Here's what I recommend. In each of your denominators, look for the bigger factorial. This 10 factorial over 6 factorial, I can cancel out the 6 factorial part and be left with 10 times 9 times 8 times 7 on top. So I'm thinking of this first part here as 10 times 9 times 8 times 7 over 4 factorial. Because that's what this part right here is. Because the 10 factorial over 6 factorial, the 6, 5, 4, 3, 2, 1 part cancels out. And then similarly here, the 18 factorial over 15 factorial is just going to be 18 times 17 times 16. And then you still have the 3 factorial on the bottom. Basically, you should have the same number of terms in the numerator as in the denominator. 1, 2, 3. 3 times 2 times 1. 1, 2, 3. 4, 4. Here, 28 factorial, this one, okay, it's going to be kind of gross. 28 factorial over 21 factorial is going to be kind of a lot here. It's going to be, oh, and flipping multiplying. So it's really 7 factorial times 21 factorial over 28 factorial. It's still not nice. And this is, I would never expect you would have to simplify something like this. It might be nicer if you're trying to write it in web work. But here I've got 10 times 9 times 8 times 7, 4 times 3 times 2 times 1, 18 times 17 times 16, 3 times 2 times 1, and then yeesh. 7 times 6 times 5 times 4, 3 times 2 times 1, and then 28 factorial, and the 20 factorial on top leaves me with 28 and 27, 26, 25, 21, 23, 22. I would only ever do this. Like, I'm using chalk. I'm like, why is it like going crazy over there? It's because of all the chalk dust, probably. I would only ever actually write this out if I was asked something, right? You should definitely leave your answer like this, as far as I'm concerned. If we had to simplify it, we could do this, and then you can even start canceling more stuff. Like you could be like, all right, 7 and 4 is equal to 28. And I don't know. 8 is equal to 4 times 2, and 3 times 3 equals 9, and blah. You could do more, I guess. I don't really want to. How about 22? I guess not everything cancels. Yeah, I was like, I was thinking of something else already. But you could cancel more things, then if we get this reduced to something. I guess 3 for 9, then 2, that cancels, and this, I don't know. Right, it's kind of 2 times 6 times 2 is 24. You can keep going. But it's kind of stupid at this point, right? You don't really need to do all this. You should leave it like.
So, the bottom, of the 10, 4, 18, 3 should add up to 98.
Like this and this, you mean? Yeah. Yeah. Because we were picking 7 altogether, right? 4 red and the other 3 not red. Yeah. Yeah, I would agree with that totally.
Then is it fine if we write it with like the C instead?
Yeah, that should be as long as it's fine with your professor, right? Whatever your professor says is fine, it's fine. So it should be fine. Write it as some people write it like this, like 10, choose 4, and then times 18, choose 3, over 28, choose 7. That should all be fine. It still means the same thing. Yeah. Cool. All right. Are there other questions from the homework that we should look at? So I'm happy to. But I can also look at this. Oh yeah, let me grab. I feel like, did you have a question? You looked like you had a question. Yeah, sorry if you don't. You looked like you were kind of about to raise your hand. That's okay if you weren't. I just thought I saw a potential question. 6. Sure. I mean, maybe. Well, number 6 from the homework. So what do we got here? Oh yeah, this one's kind of fine. You're welcome. Also, I will post solutions to this handout, so if we don't get to much of it, I should already post solutions to it. So you can also look there. Number 6. You tossed a fair coin 9 times. 9 times. We're asked, what's the probability you get no more than 8 heads? So the probability that the number of heads is less than or equal to 8, right? No more than 8, given that at least one result is a head. Given that the number of heads is at least 1. That's our conditional probability that we're calculating. Now, there's a couple ways to do this, as there always is with conditional probability. One way is to kind of think about our reduced sample space. So if we know, if we're living in the space where at least one coin is a head. Well, there's a lot of ways that can happen. You could either get 1 head, or 2 heads, or 3 heads, or 4 heads, all the way to 9 heads. What's the only thing you can't have? 0 heads. Okay, let me ask you. If you're tossing 9 coins, or you're flipping 9 coins, how many ways can you flip 9, or how many possible outcomes are there when you flip 9 coins? Not quite 9 factorial. It's a bigger number than 36. So if I flip 1, 2, 3, 4, 5, 6, 7, 8, 9 coins, how many possible outcomes are there when I hit the first coin? It's exactly 2 to the 9. So the number of possible outcomes is 2 to the 9th. Okay. Of those 512 outcomes, how many of them have 0 heads? How many ways can you toss 9 coins and get 0 heads? No, I disagree.
Oh, wait.
You're close. You're very close to the right answer.
Yeah.
1. There's 1 way of getting 0 heads. All tails. But there's only 1 way of getting all tails, right? Each coin has to be tails. Another way to think about this is, if you like, is you're flipping 9 coins, and I want 1 tail. I'm going to do 9. Sorry. Oh, back up here. I'm flipping 9 coins, and I want 0 heads. I'm going to do 9, choose 0. Or 9, choose 0, which is equal to. So, if at least 1 coin is a head, there are 2 to the 9 minus 1 ways of that happening, which is 501. Right, the 9 choose 0, right? Because we're not including the 0 ways of getting, or the 1 way of getting 0 heads. Let me ask you a different question. So there's 1 way of getting 0 heads. How many ways are there getting one head if I'm flipping 9 coins? How many ways, if I flip 9 coins, could I end up getting one head?
One head out of the 9.
Right, one head out of the 9 coins. Exactly one. Exactly one head. 9 ways. Either the first coin is a head, or the second coin is a head, or the third, or the fourth, or the fifth, or sixth, or the 10th. Which is 9 choose 1. How many ways can I get exactly 2 heads out of 9 coin flips? I choose 2. Each of these things, the number of ways of getting them is exactly 9 choose whatever the number of heads is. So the total number of possible things that can happen if I'm flipping 9 coins is 2 to the 9th different things, or 2 to the 9th different possible ways of them flipping. And only one of them is the thing I don't have. I don't want. Want's not the right word. It's not my. Only one of them is not in my given sample set, right? Because we're saying what's the probability of having less than or equal to heads, given that there's at least one head flip. So we are living in the space of at least one head was flipped. Right. The given is saying we are in a situation where we know at least one of the coins is a head. So the only thing that couldn't have already happened is flipping 0 heads. Everything else could have happened. You could have flipped 1 head, or you could have flipped 2, or you could have flipped 3, or you could have flipped 4, or you could have flipped 5, or 6, or 7, or 8, or 9. So what we're saying is, given that you know you flipped 1, or 2, or 3, or 4, or 5, or 6, or 7, or 8, or 9 heads, given that we're in this situation where one of these things has happened, what's the probability that we flipped 8 or less heads? Well, we're living here. You're out. This is only one way of getting it. And now we're asking, given that we're living here, what's the probability that one of those things happens? So let me ask you. I'll tell you all. 2 to the 9th is 512. Just to make life easy, so we can write the numbers. So there are two of the possible total things that can happen. How many things are in my given? There's only one of them that can't be in there.
No, 8.
There are 511 different possible ways I can flip 9 coins and get at least one head. It's a lot, right? It's literally 9 choose 1 plus 9 choose 2, 9 choose 3 plus 9 choose 4, all the way to 9 choose 7 plus 9 choose 8 plus 9 choose 9. No, we already subtracted. We didn't do the 9 choose 0. Right, this one is missing. That's our 9 choose 0 that we're not including.
I put that in the web.
Well, we're not done yet. So this number is the total number of things that can happen in our, right, that's the given, right? But the probability we're trying to calculate is the number of things that we want. The number that we want out of total number possible. Bottom is 511. Okay, how many ways can we get what we want? Well, what do we want? That's a good question. The number of heads to be how many? That's one good yes, and less than or equal to 8. So what we want, not 2 to the 8. So let's think about it this way. This whole thing was 512. 2 to the 9th. We subtracted off this one, literally 1, 9 choose 0 equal to 1. And saw that the rest of these, there's 511 ways of getting it. And now what else do we not want?
Oh, the 9.
We want to subtract out the number of ways of flipping 9 heads. Flip 9 coins. How many ways can all 9 of them be heads? 1 way. Don't want you either. That's our answer. Now, I want to point out that you could approach this in a slightly different way, although it's the same. You could also approach this from a more formulaic perspective, from a probability of this and this. So the number of heads is less than or equal to 8, and the number of heads is greater than or equal to 1. Or in other words, the number of heads is between 1 and 8. That's exactly what we circled in red up there. Divided by the probability that the number of heads is greater than or equal to 1. Now, if we actually calculate it in a probability way, the probability that the number of heads is greater than or equal to 1 is 1 minus the probability that the number of heads is equal to 0. I want to make sure everyone's cool with what I just said there. I'm just taking this and rewriting it as that. Okay, so I'm asking a slightly different question than we've been asking. I don't want to know the number of ways I can get 0 heads. I want to know what the probability of getting 0 heads is. Well, first one's a tail, 1/2 probability. Second one's a tail, 1/2 probability. Third one's a tail, 1/2 probability. Probability of getting 0 heads is 1 over 2 to the 9th. One way out of 2 to the 9th total possible outcomes. Okay. And if I want to find the probability of getting between 1 head and 8 heads, that's the same as 1 minus the probability of 0 heads, and also minus the probability of 9 heads. Probability of 0 heads is again 1 over 2 to the 9th. Probability of 9 heads is also 1 over 2 to the 9th. It's the same calculation, just looked at differently. But if you wanted to make this easier, because I don't like dividing by 2 to the 9th, you can multiply the top and bottom by 2 to the 9th. And then this would equal 2 to the 9th minus 1 over 2 to the 9th minus 1. Which is exactly 510 over 511. And this problem is definitely about the complement, though. It's about not calculating what you actually want, but about calculating what you don't want and subtracting that from the total. Oh yeah, this one. Yes to your question, but I need to look it up because I've got this printout that doesn't show all the things. So I know we talked about one like this last time, but let me grab it real quick. Sorry, 1 second. Someone asked about problem 15, so we can look at that one for sure. I can find it here. 1 second. Ooh. Problem 15. Sure. Yeah, we can do that. Are there questions about this though? Okay. Here's a problem 15 says, or at least my problem 15. Screening test for disease shows a positive result in 92% of all cases when the disease is actually present, and in 1% of all cases when it's not. So what I would write, parsing that information, is the probability of a positive test given that the disease is present is equal to 92%. And the probability of a positive test when the disease is not present is 1%. And then if the prevalence of the disease is 1 in 300, probability that a random person has the disease is 1 out of 300. What is the probability that the individual actually has the disease? Wait. Oh, no, I read that wrong. I apologize. That's very careful, important to read the question. If the prevalence of the disease is 1 in 300 and an individual tests positive. Yeah. So they're asking, I don't love that is a poorly written sentence. Because because they're making it sound like, so they should have just said blanket sentence. The prevalence of the disease is 1 in 300, full stop, period. Then they should have asked, if an individual tests positive, what is the probability that the individual actually has the disease? Meaning, what's the probability of having the disease given a positive test? This is yes, but I'm using it for positive. But I like you could use a different symbol here. I'm using that to mean a positive test. You could write you can say positive. Or we're not adding there, we're just using it to represent something. So this is a classic Bayes formula situation. You're given one conditional probability, the probability of a positive test given the disease, and you're asked to find the reverse or converse probability of the disease given a positive test. And I personally think using a tree is the most straightforward way of approaching a problem like this. So covered up my screen, so I can't see what you all. Let me minimize this here for a second so I can make sure you can see what I'm writing. Yeah, we should be all right. Okay, so in our tree, we got a couple branches. First, someone either has the disease or they do not. You can branch either way, meaning you can start with having a positive test versus not, but typically the sensible way to do things is your first branch should usually be the given information that you have. Meaning, if I know a person has a positive test, given that they have the disease or not having the disease should be where things branch first. And then after that, we're going to branch into having a positive test or a negative test. Having a positive test or a negative test. All right, so now I'm going to write my probabilities. Probability of having the disease is 1 out of 300, which means the probability of not having the disease is 299 out of 300. And then if I have the disease, right, if I'm on this top branch and I have the disease, the probability of a positive test given that I have the disease is 92%, 0.92. Which means the probability of having a negative test given that we have the disease has to be what? Right. Because everything has to add up to 1. Similarly, probability of having a positive test given that we don't have the disease is 1%. The probability of having a negative test given that we don't have the disease is 99%. So now we're asked to find the probability of having the disease given that we have a positive test, which I would certainly use the conditional probability formula and say that's equal to the probability of having the disease and having a positive test divided by the probability of having a test. And while you certainly can expand this out into more of a formula, I don't think you need to. Meaning, I think we can use I know we can use our tree to just calculate what we want here. So if I want to find the probability of having the disease and having a positive test, I'm going to find, I'm gonna find that path. Well, here's the path of having a disease and having a positive test. So that's gonna equal. Well, it's an and, so it's the probability of having disease, 1 out of 300, times the probability of having a positive test given that I have a disease, 0.92. Divided by the probability of a positive test. Well, there's two different ways I can get to have a positive test. I can either have the disease and have a positive test, or I can not have the disease and have a positive test. So I can have the disease and a positive test, meaning it can be a 1 out of 300 times by 0.92. Or plus, I cannot have the disease and still have a positive test. And that's how we calculate this. It's a very standard type of calculation for this situation. What do you mean by the total probability? Well, I did. So I didn't write it out. So you're totally right. So what I'm really doing here is I'm using the formula. So for the intersection here, I'm really using this formula. For probably having disease and a positive test, it's really the probability of having a disease times the probability of a positive test, given that we have a disease. I just didn't write that out. I just looked at my tree diagram to calculate that. And then similarly on the bottom, for the probability of having a positive test, I used the law of total probability. I said there's a probability of having the disease and the positive test, or having the disease and not having the disease and having a positive test. And then furthermore, I use this formula again to get each of those, to get each of those. Right, this is really probability of having the disease times the probability of the positive test when you have the disease. And it's really probability of having not having the disease times the probability of the positive test when you don't have the disease. Again, unless your teacher is specifically asking you to write this formula out, I really think writing it as a tree is the way to go. I feel like it's the most concise way of really getting all of your data into a really easily readable form. And also, if you're thinking about like trying to get to what you're being asked for, like you're trying to get to a positive test, you can kind of just follow the path and be like, oh, well, I have to go here, then I have to go here, that times that. And then I have to go here, and then I have to go there, that times that. I think it's a sensible way of getting there. Doesn't mean you couldn't use the formula. The formula also totally works. It's just not, I mean, I've done it enough times at this point in my life. For many years, I've looked at this formula and I finally memorized it, but it's not something that was easy for me to memorize when I first learned it. So I would recommend the tree, but also memorizing a formula is totally fine. Cool. All right. What time is it? 2:33. Terrible weather today. Not terrible, just doesn't look very inspiring. Is there anything from this final review we should look at? He said before looking over it. I think about what's going to be on your final. Has your teacher given you indications as to what your final is going to look like? Oh, no.
Except
It's
like.
a mystery.
It's a mystery.
I don't know change it because I don't think the strike will be over.
Right. So what do you mean by you want to change?
He said that there's gonna be a lot less probability and
Okay.
stuff because we haven't had discussing sections.
That's fair. Yeah.
He said like the extent of like difficulty of probability is gonna be like equivalent to the homework and like he's showing us and like
Okay.
basically the.
Sure.
And he also said that overall it'll probably be shorter.
Well, yeah, right. Yeah, I get that.
No, if he does that.
Multiple choices.
No,
No, you don't, nobody wants a multiple choice.
My friend who's in 2019, like, oh, canceled. No. Yes. Like, I'm not doing this.
Wow. That's
Jealous.
surprising.
I know, I.
The problem is a lot of people are trying on the final, but hopefully we're up.
But it's like.
Right, so-
Answers. I really.
Oh, well, that's super helpful.
I can actually get an A minus sometime.
Let's see here. Look at this. Oh, we did that already, yeah.
James, quick question, for 7.
Yeah,
What's the new? That's like a fancy name for something that we are.
for 7,
Yeah, number 7 on like the final review problems, like.
you should probably ignore that. No, that's not true.
I don't think he said like.
Sure. No, yeah, we didn't cover nonlinear difference, we didn't cover nonlinear. So I will tell you, just to do, yes. The Jacobian is just the matrix of second part. So it's yeah,
Okay, so number 7, we kind of just don't know.
yeah, you shouldn't worry about 7. Yeah, it's too bad, because it's kind of interesting, but yeah. Yeah.
Yeah.
No, it's the first part.
Do that.
For the disease part, we just did,
Yes,
there's a problem on homework like number 7, where it says if the test is administered to a randomly chosen individual, what is the probability that the result?
sure. So
How would you approach that?
that question is like the easier version of the question we just did. So in the question we just did, we answered the question, what's the probability that the person has the disease given the test positive? And it was equal to the probability of having the disease and testing positive, divided by the probability of testing positive. This is what they are asking to calculate. The probability of testing positive. The probability of testing positive, that's where you're using the law of total probability. And you're saying it's the probability of either having the disease and testing positive, or the probability of not having the disease and testing positive. Which is less term. I would still use a tree though. I would still be like, disease, not disease, positive, negative, positive, negative, and you're just trying to do that and that. Yep, much better. Other questions? Yeah.
Maria is literally the person who knows how to-
Sorry, what was that?
They all literally rely on this.
Number 8.
Is like no longer. No, she's gone. Oh, it's like not long, it's like.
Number 8.
It's like pretty-
Yeah, I gotta. Sure. Ah, cool. Yeah, so here's a different style of Bayes formula S question. The same sort of thing, but a little different. Screening test for disease shows a positive result in 94% of all cases when the disease is actually present. So probability of a positive test given that the disease is present is 94%. And then gives a positive result in 2% of all cases when it is not. The probability of a positive test given not having a disease is 2%. This is number 8. When the test is so different information here. When the test is given to a large number of people, 35% of the results were positive. They're telling us the probability of a positive test is 34%. And they're asking us, what's the prevalence of the disease? Or in other words, what's the probability that a random person has the disease? So that's the setup here. Okay. So I feel like this is a lot of probability.
Oh, that's what I was thinking. For the last one, the
The one we just did was the probability of having a disease, given that you have the positive test.
that's just right there.
That's a conditional. This is not conditional. So, yeah. Huh.
Oh, wait, didn't Dr. Chaudhary do this yesterday? Yeah, he did something like this.
Sure. I kind of want to go tree here. Yeah, let's do a tree. I've always loved tree. But I think we want to reverse the order of our tree. Usually I do disease, not disease, but here I want to do positive, negative. We know the probability of having a positive test is 34%, which means the probability of someone having a negative test is 66%. And similarly, well, not similarly, given given that someone has the disease, the probability, sorry, I don't love that. No, I don't like that at all.
He did it like a really weird.
Yeah,
He did it really, really weird. He did use a lot of total probability.
sure. I mean, okay, here's the thing, here's the thing we actually do. We're trying to find the probability of having the disease. And I'm gonna use that. I would say the probability of a positive test, given that having the disease, is equal to the probability of a positive test and having the disease divided by the probability of having the disease. Right? So again, we can talk like. Okay. Good. So. Yeah. Yeah. This one's always kind of fun. Oh. Is that easy? See here. Now I'm feeling like kind of wonky. Okay. Sure. All right. So. Yeah, okay, yeah, this one is kind of weird. I think.
Like we set it up as like when the probability of having disease, like a variable.
Right, yeah, totally. So, let's call that X, it's easier, right? And. Yeah, I have to think about this for a second. Sorry, it's been a while since I know I've done this kind of question before, but it's always kind of backwards, so it's harder to think about what's happening here. Well, I guess we could just. Base formula. Yeah, we do that. So here's, I guess, what I'm thinking about. So let's say we want to find the probability. Given that we have a positive test. I'm just kind of thinking, you might not want to write this, I'm just kind of thinking about how we might get there. So we would do this in the usual way. And then, yeah, we would use that, which is going to be the probability of having a positive test given you have the disease, times the probability of having the disease, divided by logical probability, same deal. Was there anything weird? I mean, well, yeah, obviously, but anything that doesn't make sense. Sorry, I hope you guys see over here. I know it's not great. I'm just using the logical probability. I'll try to write it over here in a second. So we know what most of these things are. Well, maybe not most of them exaggeration. But I know. Yeah, I'm not. Yeah, I feel like I'm missing some key step here.
Do you think you could have put this on the?
No, but still, it's a homework question.
Oh, yes. So I would say.
I'm forgetting about something.
I feel like if it's, you're seeing it twice, I feel like.
Yeah.
It's good. Yeah, because I feel like there's.
Let's make sure we're reading the question right. The problem, this is question 8. So the screening test for disease shows a positive result in 94% of all cases when the disease is actually present. So probability of a positive test given the disease is 94%. And it also shows a 2%, so it shows a positive result in 2% of all cases when the disease is not. So probably a positive test given not having the disease 2%. Okay. When the test is administered to a large number of people, 34% of the results are positive. So the probability of a positive test is 34%. And the probability of a negative test is not necessarily need that, but it's worth throwing out there. And then finally, what is the prevalence of the disease? What's the probability that someone just has the disease? Okay, let's go a different direction here. Let's go this way. So the probability of having the disease is equal to the probability of having the disease and a positive test. What's the probability of having the disease? No, okay. I think I know what. Now, finally, I think I figured it out. Okay. Here's the thing we actually want. Probability of positive test is probability of positive test and having disease, or the probability of a positive test and not having disease. True. Cool. Okay. So then we can write this as the probability of having a positive test given to have disease times the probability of having the disease.
Yeah, that's how we.
Plus the probability to have a positive test given to have the disease times the probability to have the disease. And now let's fill in what we know. Probability of having a positive test is 0.34. Probability of a positive test given the disease is 0.94. Probability of having disease is what we're trying to find. Probability of having a positive test given you have the disease is 0.02. The probability of not having the disease is 1 minus. And then we can solve for x. So 0.34 equals 0.94x plus 0.02 minus 0.02x. So 0.92x is equal to 0.32. Yeah. And then divide. So x is going to be 32 over 92. Or whatever that reduces to.
I ended up getting like 35.
That seems about right. Yeah. Like it's 32 out of 92 is a little bit more than 32% because it's not 32 out of 100. Yeah, that seems right. You could write it as 0.32 out of 0.92, but I just multiplied by 100. So yeah, so it's a little bit tricky, right? Because you don't start. So I think the challenging part about this problem is that you're asked to find the probability of a random person having a disease, right? You're asked to find probability of a disease, but you don't start off by using the formula for that. Right? I didn't start off by finding the probability. I tried to, it was failing hard. Right, you have to start off by finding the probability of something you guys already know, the probability of having a positive test. So that one's a little bit tricky. I don't know how to make it not tricky, other than to remember that if you're doing kind of the weird thing, right, where you're not finding what you usually have, because usually in these sort of situations with base formula, you're usually given the probability of having the prevalence of disease. So if you recognize that you're not given that, you might think, oh, that's like that weird thing where instead of trying to calculate this directly, start by using the law of total probability for the probability of having a positive test. Then you'll get mostly things you know. And then the things you don't, really, this is just 1 minus the things you don't. You're only getting one unknown, which is perfectly solvable. Yeah, it's a little funky. All right. It's 2:50. You can probably call it a day. I mean, unless you have other questions. Like, I'm happy to answer the questions, but it's also not.
Sorry.
No, you're good. Totally. Yeah. Yes. Sure. Yeah. Let's take a look at number 4. And this was something we did do a little bit of. Right? We did? I think we did. I don't know. It's always hard to remember what every class covers. I know it's only been one class.
I know it was in the,
Okay,
I remember.
so let's look at both of these, because they're not too terrible. Maybe one of them's terrible. The limit x y approaches 3, 3 of x squared minus y squared over x squared minus x. So my bet here would be that this limit probably exists. And the reason why my bet is that it probably exists is because usually when we show a limit doesn't exist, we show that there's different paths through the point that gives you different values. The problem is usually the path, the point we're going through when we find different paths is 0, 0. Because it's easy to find paths to go through 0, 0. Y equals x squared, y equals x cubed, x equals square, right? All kinds of things. Whereas finding paths to go through 3, 3, not that it's impossible, but it's certainly more work. So that's why I'm thinking it's probably going to be existing. So if you plug in 3, 3 right off the bat, you get 0 over 0. So I'm going to look and see if does this factor into it. And yeah, I get some factoring. Right, and this is only because I'm pretty sure it's going to actually equal something. So if I factor the top, the top factor is x minus y times x plus y. Factor the bottom, I factor out an x and left with an x minus y. And then the x minus y's cancel out. And so then we're left with the limit as x, y approaches 3, 3 of x plus y over x, and then we just plug in and we get 3 plus 3 over 3, which is 2. Now the other one is a different bag. The other one is the limit as x approaches 0, 0 of 4xy over x plus y squared. I have feelings about this. Let's see. So my go-tos are first and foremost always trialing y equals 0 or x equals 0. That's one that people often forget about that produces usually something. So if we set y equal to 0, right? Because the line y equals 0 definitely goes through the origin. Oh, sorry, that's approaching 0, 0. Sorry about that. That's kind of important. Right? Y equals 0 definitely goes to the origin. So if we set y equal to 0, then this becomes the limit as x approaches 0 of 4 times x times 0 over x squared plus 0. And if we simplify this, oh, I don't think it's going to work. Bummer. Usually it does. Oh, no, it's going to work. I'm a liar. It totally works. What's 4 times x times 0? And what's x squared plus 0 squared? Right. What's 0 divided by not 0? Right. This is the limit of x equals to 0 of 0. Most of the time, not always, but most of the time when you plug in either y equals 0 or x equals 0, you end up getting the limit being 0. Not 100% of the time, but often. On the other hand, let's pick a different path that goes to the origin. Like, I'm betting y equals x is going to do something different. And I'm betting on that because when I plug in y equals x, I'm essentially going to get x squared on top and x squared on the bottom. If the degrees are the same, it's usually a pretty good bet you're going to not. So if I do that, limit as x approaches 0 of 4 times x over x squared plus x squared. That's the limit as x goes to 0 of 4x squared over 2x squared. The x squared cancel, and the limit of 4 over 2 is just 4 over 2. And now, since we have two different paths that have different values, the overall limit does not exist. It's kind of like the left and the right hand limit not being equal to each other. The overall limit doesn't exist. Typically, that is usually what happens when you have a limit that's going through the origin. Is most of the time you're getting two different paths that have two different values, and one doesn't exist. All right, let's call it a day. I'm gonna head over to CADS, and yeah, it's been great having you all. Good luck on your last math final. Maybe ever, maybe double math for a kid.
Oh, he's sad.
You can find me for all this.
Next quarter. I need one time a day. Yeah, yeah. Psych, O10,
All right.
2.
See you all later.
Oh. Fixed, that's what it is. Oh.